Bismillahirrahmanirrahim. I'm Amal Suhail and my roll number is 21TE04. Today I'll be implementing Lab 8 of Digital Signal Processing, which is about moving average filters and Fourier transform design method of FIR filters. The objective of this lab is implementation and analysis of moving average filter, implementation and analysis of finite impulse response filter Fourier transform design method. Task 1 of the lab is define a filter, types of filters, what are the time domain parameters for a filter, what are the frequency domain parameters for a filter, and discuss the role of low pass filter for filter design. Here we can see the task 1, which is define a filter. Filters are devices or processes used to remove unwanted components or features from a mixture, signal, or dataset. They can be applied in various contexts, each with a specific type of filter. Filters have two uses: signal separation and signal restoration. Signal separation. Signal separation is needed when a signal has been contaminated with interference, noise, or other signals. For example, imagine a device for measuring the electrical activity of a baby's heart while still in the womb. The raw signal will likely be corrupted by the beating and heartbeat of the mother. A filter might be used to separate these signals so that they can be individually analyzed. Then comes signal restoration. Signal restoration is used when a signal has been distorted in some way. For example, an audio recording made with poor equipment may be filtered to better represent the sound as it occurred. Now, the task B is types of DSP filters. Low pass filter. It allows frequencies below a specified cutoff frequency to pass through while attenuating higher frequencies. Its applications involves removing high frequency noise from audio signals, smoothing data, and anti-aliasing in digital audio. Then comes high pass filter. It allows the high frequencies to pass through them and attenuate the lower frequencies, and they are helpful in removing low frequency noise or hum from audio signals, enhancing high frequency components. Then comes band pass filters. It allows frequency within a specified range to pass through while attenuating frequencies outside the range, and its applications involves isolating specific frequency bands in audio signals, radio communications, and medical signal processing. Then comes band reject or band stop, which is also called notch filter. It attenuates frequencies within a specified range while allowing frequencies outside that range to pass through. And its applications are removing specified unwanted frequencies such as 6 Hz, power line noise, and biomedical signals. And then comes the time domain parameters for a filter. There are 3 time domain parameters for a filter, that are step response, overshoot, and non-linear phase or linear phase. A filter will be considered as a good filter if it has a fast step response. A filter is a good filter if it do not have the fluctuations at its edges, which means it do not have the overshoot. Linear phase represents that it should be symmetrical. The filter should have symmetrical rising and falling edges, which means a filter is considered to be good if it has a linear phase. Now comes the frequency domain parameters for a filter. There are also 3 frequency domain parameters for a filter, which are roll-off, ripples in pass band, and stop band attenuation. Roll-off: if the filter has a fast roll-off, the filter is considered to be a good filter. And if it has fluctuations or ripples in its pass band, then the filter is a poor filter, so it should have a flat pass band. Then comes the stop band attenuation. If the filter has a good stop band attenuation, which means that its side lobes magnitude decreases with increasing frequency, then a filter is considered to be a good filter. The task E of the first task is discuss the role of low pass filter for filter designing. Low pass filters play a foundational role in the design and implementation of various other types of filters in digital signal processing and analog signal processing. A low pass filter can be converted to high pass just by spectrum inversion. Band pass filter can be designed using a low pass filter and involving its output by its inverse, that is high pass. And band reject filter can be created by spectrum inversion of band pass filter, or we can also add the low pass output and its inverse output in parallel. Task 2 of the lab is plot the signal in time and frequency domain along with its magnitude response. Firstly, apply 3-tap moving average filter, then apply 11-tap moving average filter, and then apply 25-tap moving average filter and observe the outputs. Let us see the MATLAB code. Here we can see that this MATLAB code defines a signal X, which is initially a zero array with segments set to 1, creating a rectangular pulse from indices 41 to 120. Noise is added to the signal, producing X noise. 3 different moving average filters, 3-tap filter, 11-tap filter, and 25-tap filters are then defined and applied to the noisy signal using convolution, resulting in filtered signals Y3, Y11, and Y25. The code plots the noisy signal and the filter signal to compare the effects of different filters, and it computes and plots frequency responses of the 3 filters using the frequency z function. Let us run the code. Here we can see the magnitude and phase responses for the 3-tap, 11-tap, and 25-tap filters. Firstly, we can see the original noisy signal, then 3-tap moving average, then 11, then 25. The results show that the 3-tap filter slightly smooths the noise, the 11-tap filter provides more smoothing, and 25-tap filter achieves the most smoothing but also causes the most delay and blurring of the signal edges. The frequency response plot reveals that as the number of taps increases, like it is of 3-tap filter, then comes 11-tap filter, and then 25-tap filter. So it shows that as the number of taps increases, the filter's ability to attenuate high frequency noise improves, but the transition from pass band to stop band becomes less sharp, indicating a trade-off between smoothing and signal distortion. Here is the task 3 of lab 8, which is repeat example 7.2 with 7 tap, 17 tap, 51 tap, and 101 tap. Observe the frequency domain parameters. So in example 7.2, we have to calculate the filter coefficients for 3 tap filter, 3 tap FIR low pass filter with a cutoff frequency of 800 Hz and a sampling rate of 8000 Hz using Fourier transform design method. Then determine the transfer function and difference equation of design FIR system and plot the magnitude response for 0, pi by 4, pi by 2, 3 pi by 4, and pi radians. Let us see the MATLAB code. Here we can see this MATLAB code designs and analyzes low-pass FIR filter with different number of taps 3, 7, 17, 51, and 101 and a cutoff frequency of 800 Hz giving a sampling rate of 8000 Hz. The normalized cutoff frequency WC is calculated and the filtered coefficients H are determined using the sinc function. Then for each value of m, the filter's frequency response is computed by evaluating its transfer function h over a range of frequency w from 0 to pi radians per sample. The magnitude of the frequency response is then plotted for each filter, highlighting how the filter's length m plus 1 coefficients affect its performance. Points at specific frequencies 0, pi by 4, pi by 2, 3 pi by 4, and pi are marked on the plots to show the filter's frequency response at these key frequencies. Now let us run the code and observe the output. 101 tap filter, 17 tap, 51 tap, and 7 tap, and 3 tap filter. Here we can see the output reveals that filters with more taps have a sharper transition band, which means that, for example, a filter with 101 taps has a sharper transition band and better attenuation of frequencies beyond the cutoff, resulting in more defined and efficient low-pass filter, although at the cost of increased computational complexity and filter delay. Now the part B of this lab task is apply the filters made in the part to signal X. Signal observe the changes for signal X in time and frequency domain while varying the number of coefficients of the filter. So let us see the MATLAB code. Here we can see the MATLAB code generates a composite signal X composed of 3 different sinusoidal signals with frequencies 1100 Hz, 1500 Hz, 2100 Hz, 2200 Hz, and 3700 Hz sampled at 8000 Hz. The signal is then filtered using FIR low-pass filters with various number of taps 3, 7, 17, 51, and 101. For each filter, the sync-based filter coefficients H are calculated. Here we can see. And at a cutoff frequency of 800 Hz, the signal is filtered by convolving signal X with these coefficients, and the filter signal Y is plotted. Additionally, the magnitude frequency response of each filter is computed using frequency Z and plotted, and the resulting figure is represented here. The resulting figure displays the original signal and the filter signals, showing how increasing the number of taps in the FIR filter progressively improves the attenuation of high frequency components, thereby demonstrating the effect of filter length on the ability to isolate the desired low frequency components. Now the task 4 of the lab is repeat example 7.3 with 7, 17, 51, and 101 tap filter. Observe the frequency domain parameters. Firstly, we have a 5 tap filter with a low cutoff frequency of 2000 Hz and upper cutoff frequency of 2400 Hz and sampling rate of 8000 Hz. We have to plot the transfer function and frequency responses with MATLAB. Let us see the MATLAB code. Here we can see that this code generates a composite signal X, consisting of multiple sinusoidal components with frequencies 1100, 1500, 2100, 2200, 3100, and 3700 Hz, sampled at 8000 Hz frequency. Then, the filter coefficients H are calculated using the sync function for cutoff frequency of 800 Hz. For each filter, the signal is filtered by convolving signal X with filter coefficients, and the filter signal Y is plotted. Additionally, the frequency response of each filter is computed and plotted using frequency Z function. The resulting figure displays the original composite signal, the filtered signals with different taps 3, 7, 17, and various tap filters by smoothing the noise. Thank you so much for watching. See you in the next video. Allah Hafiz.